We're going to wrap up the VSEPR theory in this video with structures that have 4 electron groups around the central atom. So previously we looked at structures that have 2 electron groups or 3 electron groups around the central atom. And we said that's really what we're concerned with. After we draw the structure, the dot structure, we want to take inventory of what's happening on the central atom. How many bonding groups? How many lone pairs? And those lone pairs still count as electron groups. And the VSEPR theory says that electron groups will repel and they'll orient themselves as far apart as possible. And that's what gives us the true 3-dimensional shape of a molecule. So we talked about the linear structure. The linear structure has 2 electron groups on the central atom. They could be single bonds, double bonds, triple bonds. They could be a combination of a single and a triple. There's only 2 electron groups on the central atom. And the farthest I can get those 2 groups is 180 degrees. If you have 3 electron groups around your central atom, they'll orient themselves as far apart as possible, and they'll go 120 degrees around the central atom. We call it a trigonal planar structure. Trigonal meaning triangle, planar meaning flat. Now, 3 electron groups on the central atom will always make me think trigonal planar, flat, triangle. However, sometimes we draw a Lewis structure and we'll find there are 3 electron groups on the central atom, but one of the electron groups is a lone pair. And so that's what this half of the table says up on top. Number of lone pairs of electrons on the central atom. So I've got a total of 3 electron pairs, but one of them is a lone pair. It's still a pair of electrons. And so it's still going to give me that trigonal planar bond angle. It's still going to give me the 120 degree bond angles of a trigonal planar structure. These are still 120s. But obviously it's not going to look the same because it only has 2 atoms. The third spot's not really an atom, it's a lone pair. And so the real structure is going to look bent. And whoever came up with this name was brilliant because it's not linear. It doesn't go 180 degrees. It's going to be like crooked. It's going to be bent. So now we want to look at the 4s. And so these are really common. Carbon loves to make tetrahedral structures. Carbon's got his 4 valence electrons. So let's give him 4 bonds, maybe like 4 hydrogen. There we go. 1, 2, 3, 4. Super easy, right? We're masters at drawing the dot structure, which is always step 1 because we have to draw the structure so that we know how many electron groups are on the central atom. So electron groups, there are 1, 2, 3, 4. There are 4 groups of electrons on the central carbon. 4 groups of electrons will orient themselves as far apart as possible and give me what's called a tetrahedron. We call it sometimes a tetrahedral shape. It looks like this little guy down at the bottom. It's kind of like a rocket ship. What's really interesting is that the angles are all the way around. I mean, they're trying to draw a 3-dimensional here. The angles are 109.5 degrees. Do you have to memorize 109.5? No. But here's what I do want you to know. I want you to know that the angles are not 90. They're not 90 degrees. I mean, when we draw our structure on paper, look at my Lewis structure. It looks like this is a 90-degree angle, right? And that's how we draw our dots. It looks like a flat cross on paper. Well, yeah, on paper, I don't have to draw this thing looking like a little rocket ship. And that would just get tricky with us trying to draw things in perspective. We don't have to draw to the proper angles. But in my head, I need to think about this. I want to put those four groups as far apart as possible. But I can go in 3 dimensions all the way around the central carbon. I don't have to stay flat on paper. Yeah, maybe on paper, the farthest I can draw them is like what I have, maybe looking kind of like a 90-degree angle. But in real life, I can do better than 90. I can go almost 110 degrees. And you can kind of tell, right? Like when I look at this structure here, when I look at like the little picture with the sticks and balls, can you tell if that's more than 90 degrees? Yes, it's because we want to put those electron groups as far apart as possible. We can do better than 90. So it really looks like this 3-dimensional little rocket ship thing, the tetrahedron, where the angles are better than 90 degrees, farther, almost 110 degrees. Cool, tetrahedron. Most people get that one right because tetra means 4, right? All right, so now let's draw one of his buddies, NH3. How about nitrogen with his 5 valence electrons? He's got the lone pair. Let's hook on some hydrogen. 2, 3. I like that. NH3. The structure is pretty straightforward. I got this. Now when it comes to the shape and the angles, I'm counting all the electron groups in the central atom. Well, obviously there are 3 bonds, but there's a 4th electron group. There's a lone pair. So there are 4 total electron groups on the central nitrogen. That in my mind makes me think about this tetrahedral structure. It makes me picture in my mind this little rocket ship, 3-dimensional. But here's the problem. I do have 4 electron groups that are going to repel into this tetrahedral shape, but one of them's not really an atom. One of those electron groups is the lone pair. And so it looks kind of like this middle structure on the bottom. Picture up here the lone pair. And so it's kind of the same as the tetrahedron, but we call it the pyramidal, or sometimes you'll hear it referred to, like there's usually a word up in there, trigonal. I usually call it the trigonal pyramid or trigonal pyramidal. Trigonal still meaning that there's 3 atoms, but they're not flat. We had the trigonal planar. Trigonal planar was like 3 atoms but flat. Planar means flat. Well, here the pyramid is supposed to show that it's not flat. Can you kind of see why they would call it pyramidal? Like it's kind of raised up like a pyramid. And it's because it's based on the tetrahedral structure. It looks just like, the bottom 3 atoms look just like the tetrahedron. It's just that the top atom is missing. And so it's not a true tetrahedron. There's not 4 atoms. It's trigonal, 3 atoms, but pyramid, meaning not flat. And so again, the angles are going to be really similar to the angles on a tetrahedron. I'm going to have angles between the bonding groups and the lone pair. All of these angles are still approximately 109.5. Oh. And so we got to just be careful when we see a formula. Like here I see the formula NH3. But previously we had this guy over here, the BH3. The formulas look exactly the same. But you can't say the shape just by looking at the formula. You got to draw the structure because we need to know how many electron groups, and that includes lone pairs. So the BH3 only had 3 electron groups. They could repel as far apart as possible, 120s, 120 degrees trigonal planar. But the difference now is that in NH3, I've got a fourth electron group. So there's more repulsion. The electron groups are now going to be less than 120 degrees. They're less than 120 because I have another group of electrons. There's four things that are repelling on the central nitrogen. So the angles are actually about 109. 109.5. It's based on the tetrahedral structure. So their formulas look similar, but their shapes are not. Kind of the same thing happens when we talked about like CO2 versus SO2. The formulas look exactly the same. But once you start drawing it, you'll find that the SO2 actually has 3 electron groups, 2 bonds, but there's that third group that's a lone pair. And we don't see that just by looking at the formula. We got to draw them. Awesome. And the last structure. Check out something like water, H2O. So we draw the central oxygen with his 6 valence electrons. And then I hook on a hydrogen and another hydrogen. Whoopsies. There we go. Awesome. Okay, so I got the structure. That wasn't so bad. And now I'm looking at the central atom. What's happening to my oxygen? Well, there's the 2 bonds, obviously. Those are electron groups. But there are 2 lone pairs. 2 electron groups, 2 lone pairs. It's a total of 4. There's a total of 4 electron groups in the central atom. Well, 4 groups would make me think tetrahedral. Well, yeah, I mean, these angles are going to be close to 109.5. It's based on a tetrahedral structure, but obviously it's not a true tetrahedron because there's only 2 atoms. So it's kind of like you have to picture, let's see if I can move this out of the way, that if this were my tetrahedron, 1, 2, watch me draw this in perspective, 3, 4. It's like my little rocket ship, like my little tetrahedral rocket ship. Here would be the true tetrahedron with 109.5 degree angles. But 2 of these spots aren't really atoms anymore. So it's like if I take 1 and I take 2 and I pop them off, and instead of them being atoms, now I could say, well, up in here is a lone pair, and then down in here is the other lone pair. The remaining orange atoms are not linear, it's bent again. So there's 2 forms of bent, and the only difference is just that this bent is a little more bent than the original. So these angles, even though they're not really showing it, these angles are going to be close to 109.5. I'll see if I can kind of draw them on here. That I would have 2. Well, that's a bad dot. 1 dot, 2 dot. It would be something kind of like this, where I'm going to have 2 lone pairs. And so really the atoms that are left are not linear. So linear is if you only have 2 electron groups, and that's it. No extra lone pairs. But both of the bents have at least 1 electron group. So you still have 2 atoms, but the middle bent, this first one in the middle, this guy, has 1 lone pair, and this bent has 2 lone pairs. So anytime you have 2 atoms, but either 1 or 2 extra electron pairs, those lone pairs, it changes the shape from being linear to bent, because it provides another region of repulsion. And those electron groups are going to repel and orient themselves as far apart as possible, even if it's not a bonding electron group. So it changes the shape from being linear to bent, and it's going to change the properties of the particle. The same thing can be said about the trigonal planar versus the trigonal pyramid. Their formulas look really similar. They'll have 3 electron bonding groups on the center. But the trigonal pyramid has a fourth group that's a lone pair. And again, that's going to change the shape from being flat to being a pyramid, and it's going to change the properties. So the key to picking out the true shape of the molecule and understanding the angles is to, number one, draw the structure, and then number two, count the electron groups on the central atom. This will be like the total number of electron groups, but this will tell me how many of those groups are lone pairs. And those are really important. They'll affect the shape and the properties.